Hello, AP Chem 12. This is Mr. Chan, and today what we're going to do is we're going to talk about something called Gibbs free energy. Now, this relates back to equilibrium and the idea of how equilibrium is related to enthalpy and entropy. Okay? Now, remember, a reaction spontaneity depends on both its enthalpy and entropy. So to help predict whether a reaction is spontaneous or not, mathematically, we can combine the ideas of enthalpy and entropy into one equation called Gibbs free energy. Okay? So Gibbs free energy is delta G is equal to delta H minus T delta S, where delta G is the Gibbs free energy, delta H is the enthalpy of a system, T is the temperature in kelvins, and delta S is the entropy of the system. Now, how does this relate back to entropy? So this equation is actually based on the equation, recall from delta S, the universe is equal to delta S of the system plus the delta S of the surroundings. And remember, we had said that if delta S of the universe is positive, the reaction is spontaneous. So how does it relate to delta G? Okay, so if we had delta S of the universe, remember we can rewrite this as delta S of the system plus negative delta H over T. Remember, you learned that delta S surrounding is just negative delta H divided by T. If we take the T and multiply everything by negative T, what you have is you have negative delta S universe is equal to delta H minus T delta S. And this, oopsie, I forgot to put the negative T here. So negative T delta S universe is equal to delta H minus T delta S. And this is where it is related to delta G. Okay? Now, so delta G is temperature dependent. Notice the temperature does affect delta G. And if delta G is less than 0, the forward reaction is spontaneous. If delta G is equal to 0, reaction is at equilibrium. And if delta G is greater than 0, forward reaction is non-spontaneous. Now, why is delta G less than 0 would be considered spontaneous? Is because, remember, the delta S universe is multiplied by negative temperature. And so a positive delta S universe is spontaneous. When you multiply it by a negative temperature, it becomes a negative value. And so that's why when delta G is less than 0 or negative, it is a spontaneous reaction. Now, how do you relate delta G? So we have this little paragraph. It says, just like potential energy in a gravitational field drives a boulder until it reaches a state of minimum potential energy, the free energy of a chemical system decreases until it reaches a minimum value. When this minimum is reached, a state of equilibrium exists. So let's say you were to push a boulder over a cliff. What will happen is it will keep on going and then goes up the other side, and then it'll come back down and come back down until it has reached minimum potential energy. Same thing for a reaction. When the reactants are mixed, what happens is the free energy decreases and then goes up to the products. And then the products will react to form reactants until you have reached the lowest point free energy. And at this point, this is when we get our equilibrium. Okay, so delta G is just a mathematical way of determining whether or not a reaction is spontaneous or non-spontaneous or at equilibrium when we take the enthalpy and entropy considerations. Now, if you take a look in your textbook on page, I believe it is 812, 814, and I believe 815, you'll hear an explanation in regards to this free energy diagram. Now, free energy is a state function like enthalpy, and one can tabulate standard free energies of formations for a substance. Okay, now, if you take a look on Appendix 19, okay, you will see here is the standard formation data for different chemical compounds. Okay, now again, the little knot, the little circle in the very top means that it is standard conditions. Now, when you read through this, everything is pretty straightforward. Whoopsie, but you notice what's going on here. Okay, something's wrong with my computer system. Oops, there you go. But notice what happens is that elements in its standard state is 0. Why is it 0? Is because basically there is, when you have an element in its standard state, it's basically the most stable and there is no energy required for it to form. Now, using these standard free energies, one can calculate the standard free energy for chemical processes. Now, what you can do is take a look on page 806 to 808. So I want you to refer to page 806 to 808. Now, what's happening in page 806 to 808? So if you take a look at this, I think it is up here. Now, so here, if you take a look on page 806, they give you an example of taking delta H and delta S values, calculating the delta H for the reaction, calculating the delta S for the reaction, and then combining it into the delta G equals T delta S equation. Okay, delta G is equal to delta H minus T delta S, and to actually calculate the Gibbs free energy value, and in this case, because the value is negative, then it is a spontaneous reaction. Okay, now another way to calculate delta H is, delta G is to calculate it by individual steps. Okay, so let's say we have carbon monoxide plus oxygen gives you 2 carbon dioxide. Now, since it is a 2-step process, just like with reaction mechanisms, just like with Hess's law back in Chem 11, what we can do is combine the 2 equations, noting the first one we had to flip, the second one we had to double, and notice the delta G values was flipped or doubled accordingly, okay, depending on the reaction, okay? And they have that little description here. And then you calculate the delta G value is negative 514. So basically saying that this reaction where carbon monoxide plus oxygen gives you carbon dioxide is a spontaneous reaction. Now, if you take a look on the, I believe it's page 808, what happens is there's another way to calculate delta G, and in this case, using the summation equation. So here we have carbon dioxide and water produced from oxygen and methanol combined together. Now, again, in this particular case, what you have is you have the delta G of formation for each of the chemicals. So what in the equation, you summarize the products minus the sum of the reactants, and you get a delta G value of negative 1378. So these are a couple of few ways to calculate delta G. Now, before I move on, recall here, if I went up here, delta G was equal to 0 at reaction at equilibrium. I want to take a minute to go through one of the examples on page 801. Okay, I believe it's right up here. Okay, now, in this case, it says, whoopsie, what on earth? What is the normal boiling point of liquid bromine? This is found on page 801. I go up here, oh, sorry, page 800. Okay, now, so the one thing you need to be aware of is this goes back to phase diagrams. Now, going back to phase diagrams, whether you took Chem 11 or Chem 11 honors, you should remember phase diagrams looking something like this. Okay, and so you have your liquid, you have your gas, and then you have your liquid going to gas. Now, remember, liquid going at the phase symbols, at the phase changes, what you have is you have the two phases at equilibrium. Remembering that, notice what they did was the delta G was given at 0. Okay, so notice the delta G was 0 because it was at equilibrium. And so that's why you have 0 is equal to delta H minus T delta S. And then they were able to calculate the temperature at which it would boil, because that's the state of equilibrium. Okay, so that is something I just want you to be aware of in regards to connecting different ideas from the past and how does it apply to these equations that they give you. All right? All right, one final thing I want to talk about, and then that will be it. Okay, so scroll down, scroll down. Okay, so far we have calculated delta G under standard conditions, but most reactions occur under non-standard conditions. Now, so what we have to do is modify the equation, where delta G is equal to delta G naught plus RT natural log of Q, where R is the ideal gas constant, T is the absolute temperature in kelvins, and Q is the reaction quotient, or trial KQ. Now, for standard conditions where Q is equal to 1 and natural log is equal to 0, as a result, delta G is equal to delta G naught. Okay? Now, what we can do is we can find a relationship between delta G and K, or the equilibrium constant, can be derived as delta G is equal to delta G naught plus RT natural log of Q. Now, notice I used 0 here, because this 0, remember, is equilibrium. Okay, is equal to delta G naught plus RT natural log of K. Remember, K is the constant at equilibrium. So substituting is delta G naught is equal to negative RT natural log of K. Now, what happens is a pause. Something is wrong with my computer, but that's okay. Let's go back here. Okay, positive natural log in K means that K is greater than 1 and the reaction is more negative. Negative natural log of K means K is less than 1 and delta G is more positive. If K is equal to 1, delta G is equal to 0. Now, you might say, what? This goes back to when we talked about equilibrium. Remember we talked about K values, and we said if you have a small K cube, reverse reaction or reactance is favored. Large K cube, forward reaction is favored. So large K cube, which is greater than 1, forward reaction is favored. Take a look. When it says here, large positive K means K is greater than 1, delta G is more negative. A way you can think about this, it is spontaneous. Okay? You can have a spontaneous reaction. And here would be non-spontaneous. Okay? Now, again, goes back to our equilibrium, where you have small KQ less than 1, reverse reaction or products is favored, or non-spontaneous. Okay? Now, the other thing that we talked about here, back when we did equilibrium, here we go again. Okay. And sorry, we have a little bit of a delay here. Okay. Let's do share screen. Here we go. Okay, we're back. Remember back here where we had trial KQ, where trial KQ is greater than KQ, too much product. Trial KQ is less than KQ, too much reactant. How do we apply that with delta G? So here, this equation. Notice, if the trial KQ is less than K, what happens is that it's a spontaneous reaction. Okay? So here again is trial KQ. Okay? If trial KQ is less than KQ, it is spontaneous, or remember, it is the forward reaction. If trial KQ is larger than K, remember, it was the reverse reaction, is spontaneous. And what you want to do is you want to reach a state of equilibrium. Makes sense. Going back to this, when we did chemistry here, regular chemistry 11, okay? If you had too much product, reaction shifts towards the reactants or forward reaction. If you had too much reactant, reaction shifts towards the products, and so on. Okay? Oh, whoops. If the trial KQ was greater than KQ, you had too much product, reaction shifts towards the reactants. And if KQ is greater than trial KQ, you have too much reactant, reaction shifts towards the products. Sorry, my mistake. Okay, so that's how you relate to the two. Now, we can rearrange the equation to solve for K by K is equal to inverse natural log negative G divided by the universal gas constant and temperature. Now, remember, the E here is the inverse natural log. So here is the inverse natural log. Okay? Now, again, we had talked about this before, but you should be familiar with that particular button on your calculator, whether you are using a graphing calculator here, all right, or if you're using just a regular calculator, okay, you should be aware of those buttons. All right. Now, So let's give you an example here. So I want to take a look on page 826. I want to look at question number 69. Okay, so if we look at 826, question number 69, it says one of the reactions that destroys ozone in the upper atmosphere is NO plus O3 gives you NO2 and O2. Using the data from Appendix 4, calculate the delta G and the K at 298 kelvins for this reaction. So how would we approach this? So we have the equation. We have NO plus O3 is in equilibrium with NO2 and O2. Now, using the appendix, the data in the appendix, what you can do is you can find, in this case, NO plus O3. So nitrogen monoxide gas, NO delta G is 87 plus O3. If I look at O3, this would be 163. Here, NO2 would be 52 plus 0. Okay, so your delta G for the reaction, delta G naught for the reaction, is equal to 52 plus 0 minus 87 plus 163. And if I do that in my head, 7 minus 52 and 1, I get an answer of negative 198 kilojoules per mole. Okay, so this is a very spontaneous reaction. Now to calculate K, we would go K is equal to E negative delta G divided by RT. And so what we have to do is this would be E negative 198,000 divided by 8.314 times 298. Okay. Divided by 8.314 divided by 298. Okay. Okay, and then if we take the inverse log, so the answer would be 5.10 times 10 to the 34. Now, so looking at the K value or KQ value, you notice it is very large KQ value. That means products are favored, which is supported by the large negative delta G value. All right, ladies and gentlemen. All right. Thank you very much. Have a good day. Bye-bye.